All right, we are going to continue to think about circuits without really talking about circuits. You saw previously there we did the junction rule, sort of our physical intuition about resistivities of rods and things. Now we're really going to get awkward. Okay, I'm 48, almost 49. I live with 20-year-olds. I teach physics. I'm as awkward. I'm very good at it. Okay, wait till you see this. We're going to talk about this by talking about our body composition measurements. Yes. For real. Okay, so if you're at some exercise program or something, or at the hospital, and they want to measure your percent body fat, well, they would do it with a legitimate instrument. But if, say, you're on the line and you want to know your percent body fat, you'd buy this instrument and it looks like a steering wheel, and you hold it, and then it just shows you your body fat, your percent body fat. And you think, is this like a BuzzFeed quiz where it's just throwing up a number? I mean, how could it really work? Well, we're going to talk about how it works. So here we go. It just so happens that fat and muscle have different resistivities. So the resistivity of fat is 26 ohm meters, roughly. And the resistivity of muscle is 13 ohm meters, okay? Why? Molecular structure, water composition, free ion, something like that. Let's not worry about why. And you hold it with your arm, and it's doing it electrically. It's sending a current all the way through. But we're going to sort of just simplify it and think about like a single arm. So let's estimate an arm like this to look like a cylinder like this. And you know, in reality, of course, there's a lot of structure. There's the bone in the middle, and then the muscles around the bone, and then the fat, and then the skin. We're ignoring bones and skin. We're just doing things based on fat and muscle. And to make our calculations easier, we're actually just going to divide it like that and say part of it, the top, is fat, and the bottom is muscle. We're going to do it like that. Very nice. All right. And we're going to say, okay, I have some numbers here. We have 25 centimeters for the length of the arm, and we've got 8 centimeters for the diameter of the arm. And I have some, let's see, we're going to say X% fat and 1 minus X% muscle. All right, so X is, we'll put it here, X%, well, I'll just say fat is X%. That's like your body fat. So if my body fat was, say, 12%, then what would it, muscle would be all the rest, 88%. 1 minus X is your muscle. Okay, so we won't do it in percents, we'll do it as 0.1. So 12% body fat, 0.12. Muscle would therefore be 0.88. No brain, no bones, no skin. That's all we are, muscle and fat. Okay, so how do we do this electrically? Well, we just treat this as a circuit. We treat this as some complex resistive element. So what do? The instrument that you're holding is applying delta V to both. That was a total brain problem there. Apply delta V to both your arm fat and your muscle at the same time, and each has its own current. Each has own current based on what? Rho R equals rho L over A. R equals rho L over A. So this could be the fat part of your arm, and this could be the muscle part of your arm, like that. Okay. Yeah, so then different, I'll just put the end of the words here, different body fat composition, that's not where you split that, different body fat composition leads to different R total. The fat resistance and the arm resistance or the muscle resistance are going to kind of come together to give you an R, the resistance of your total adjusted rate mortgage, or not your total arm on your thing. Okay. Okay, so I'm gonna erase and then we'll